Hi everyone, hope you guys are doing good. Today we are going to resume our discussion on primary issues in robotic manipulators. Last time we said that rather than overly complicating the whole scenario, we're going to keep it simple and identify what are the major issues to be resolved. And this discussion is in continuation with that. So let's get started. And a quick recap of last lecture would be a good point to start. And we said that rather than overly complicating the whole scenario by using a 6 degrees of freedom robot, we're going to keep it simple. We're going to use a two-link manipulator, just like the one being shown over here. First link, second link. And at the end effector, you've got this grinding wheel, which is going to exert a specific force over this surface. And this surface, which has been defined from point A all the way to point B. So in order to achieve this grinding operation, which is going to require a specific force to be exerted, in addition to achieving all the points in between, which is going to warrant a good position control. And this whole scenario is being observed as well using a camera. So this was the whole scenario that was presented last time in order to identify all the major issues. And the first issue was that of forward kinematics. And we derived an expression for the position. So let me quickly write that one down once again. So position of end effector. So this was having x2 coordinate, which was defined to be a function of thetas, which was defined in terms of having these link lengths, which are a1 and a2. So this is going to be a1 cos of theta 1 added with a2 cos of theta 1 plus theta 2. y2 similarly is going to be another function, and in order to identify the difference between x2 function, I'm going to label this as f1 and this as f2. This is also going to be dependent on thetas, which is going to be equal to a1 sine of theta 1 plus a2 sine of theta 1 plus theta 2. So these were the two expressions to identify where the end effector is placed and how this one is oriented. Now, in addition to that, we needed to have another expression, which was corresponding to orientation of the end effector. So we were interested in that as well. And we identified last time that we were going to make use of a rotation matrix, rotation of the second frame with respect to zeroth frame, to be equal to a matrix, because it is a planar case, simple straightforward case. So it is going to be a 2 by 2 matrix. In the very first column, we said that you're going to have x2 axis oriented with respect to the zeroth frame, which is going to have two uh, mutually orthogonal axes, x0 and y0. So that is going to be x2 dot x0 and x2 dot y0. And the second column is going to be for the y-axis. So this is going to be y2 dot x0 and this is going to be y2 dot y0. So when we used the direction cosines, we were able to identify a matrix using the cosines and sine of all the thetas which are available with us. So this is going to be in that sense cos of theta 1 plus theta 2, and this was minus sine of theta 1 plus theta 2, and this is going to be sine of theta 1 plus theta 2, and this is going to be cos of theta 1 plus theta 2. We derived it in much more detail in the last lecture, so interested listeners can refer to that lecture as well. But in that, we have identified that you have two parts to be covered. One corresponding to position, and the second corresponding to orientation. So in this case, when we have a very simple straightforward two-link manipulator, this is going to become very easy to handle these two aspects. But when you grow in complexity in terms of adding more links and more joints, for example, for a 6 degrees of freedom robot, this is going to be a bit difficult problem. So in order to identify that, we're going to find out ways to do that. And this is, for that reason, termed as one of the major issues. So we will handle that in the later discussions. And the second problem was to find out inverse kinematics of the manipulator. And in that, we were able to identify if we know where the end effector should go at the next instance of time, and we wanted to compute what should be theta 2 and theta 1 values given as reference to the individual joint controls, we wanted to have these expressions. And these expressions were derived last time, and interested listeners can refer to the previous lecture as well. And these expressions for theta 2 first was this expression, where cos of theta 2 was this whole expression. And we use this expression, theta 2 expression, to compute theta 1 as well. And that was also using tan inverse. So we derived these expressions last time. Now in there, you must also realize that this is only a planar case, a very simple case, if I may say that. And what if you have n-link manipulator or multiple degrees of freedom exhibited by the robot? So in that case, this scenario is going to become more complex, and probably we will require some more interesting ways to handle these situations. And we will discuss that. For example, kinematic decoupling principle would be discussed later on. But this is one of the major issues which are needed to be resolved in robotic manipulators. Now let's focus on today's discussion. Oftentimes we need to follow a specific velocity, and sometimes we need to follow a specific acceleration as well. So for that reason, we need to take the derivative of the position kinematics, and that is going to be the topic when we discuss the differential kinematics. Now, not only that, we have to go the other way around from forward to the inverse as well. So these are the two cases that we need to discuss in much more detail, and that is going to be the third major issue. So let's explore that. So let's start from one expression that we have derived already, and that was x2 to be equal to f1 of theta, where theta is a vector of thetas, which was equal to be precise, a1 cos of theta 1 plus a2 cos of theta 1 plus theta 2. Now, if I take the time derivative of this expression, this is going to be x2 dot, and that would be equal to partial of f1 by partial of thetas time d theta by dt. And to be precise, for this whole expression, this is going to be equal to minus a1 sine of theta 1. Then you have theta 1 dot minus a2 sine of theta 1 plus theta 2. And then you have theta 1 dot plus theta 2 dot. Now, similarly, for the other expression, which was y2, which was equal to f2 of thetas, this was equal to a1 sine of theta 1 plus a2 sine of theta 1 plus theta 2. And when I take the time derivative of this was equal to y2 dot, and I can write down this as partial of f2 by partial of thetas dot d theta by dt. And to be precise, this is going to be equal to a1 cos of theta 1. Then you have theta 1 dot plus A2 cos of theta 1 plus theta 2, and then you have theta 1 dot plus theta 2 dot. Now in this case, you can see that you have two expressions, x2 dot, which I can label as expression number 1, and y2 dot, which I can label as the second expression. And I can write those in terms of vectors like x2 dot and y2 dot, both over there. And this is going to be equal to something like a matrix, and then I can separate the theta dots from that, and that I can write down like theta 1 dot and theta 2 dot. So if I can use these expressions 1 and 2, this is going to give me the expression something like this. So this is going to be the first case where you have theta 1 dot to be identified. So this is going to be minus a1 sine of theta 1 minus a2 sine of theta 1 plus theta 2. And then you have for the theta 2 expression, which is going to be equal to minus a2 sine of theta 1 plus theta 2. So what I've done, I've used these two expressions 1 and 2, and I've separated theta 1 dot and theta 2 dot terms from there. And similarly for the second row, I can write that one down. This is going to be equal to a1 cos of theta 1 plus a2 cos of theta 1 plus theta 2. And over here you're going to have a2 cos of theta 1 plus theta 2. So this is going to indicate that you have got one matrix, which is a 2 by 2 matrix multiplied with a vector, which is 2 by 1 vector of the joint velocities. And that is going to give you the end effective velocities. So if I can write this one down in a much simpler way, I can say that the vector of the end effective velocities is going to be equal to some matrix, which I'm going to call it J matrix, which is dependent on thetas, obviously, multiplied with theta dots, the vector of the joint velocities. And this is a very good expression to have in this case. We call this J matrix to be the Jacobian matrix. And these theta dots are obviously, as you can identify, these are joint velocities. And you have over here x dots, which are the end effector velocities. So you can identify that the end effector velocities are related with the joint velocities using the Jacobian matrix in the middle. So this expression is going to become much more handy expression later on as well, and we will see how the Jacobian are derived, these matrices are derived, and how we're going to correlate what is going to happen with the end effector velocities when you know what are the instantaneous joint velocities. So you can or you would use this expression frequently, and this is what we call forward velocity kinematics. And this is one part of the differential kinematics. This would mean that if you have a robot starting from your base frame, going all the way in the forward direction up to the tool center point, and if you know what is this velocity corresponding to the first joint, which is theta 1 dot, what is happening over here, theta 2 dot, what is the velocity over here, theta 3 dot, and in going forward direction, going all the way to the tool center point, and you wish to find out what is happening over here, or what is the velocity of tool center point. This expression that we have derived just recently is going to give you that expression. It is going to give you how the end effective velocities are computed when you know what are going to be the joint velocities. Jacobian is going to be computed in most of these cases once initially, and it is going to be used to transform the joint velocities into the end effective velocities. And that is the physical realization of forward velocity kinematics. So the case of forward velocity kinematics has been discussed, but what about inverse velocity kinematics? As we have discussed for the case of position kinematics, the forward and inverse cases, similarly in differential kinematics, especially in this case velocity kinematics, we need to consider both of these cases. So this is going to become a tricky scenario, but we can handle it just like using the expression that we have derived earlier. We said that the vector of the end effective velocities is going to be equal to Jacobian times the joint velocities, theta dots. Now, if I use this expression by taking Jacobian on the other side, I can write an expression for the joint velocities, or the inverse velocity kinematics expression. Theta dots, which are the joint velocities, are going to be equal to, when Jacobian taken on the other side, this is going to give you Jacobian inverse times x dot to be the expression. And Jacobian inverse, or any matrix inverse, is going to be adjoint of Jacobian, in this case, divided by determinant of Jacobian times x dot. So this is going to be theta dot expression that we are going to use to compute the inverse velocity kinematics expression. Now, as we have derived earlier, the Jacobian was this expression. We're going to make use of this expression to compute the adjoint. So if Jacobian is this, which means that the adjoint of this Jacobian is going to be equal to I'm going to change the places of this with that. So this is going to be A2 cos of theta 1 plus theta 2 at this particular location, and this element minus A1 sine of theta 1 minus A2 sine of theta 1 plus theta 2 at this particular location. And then I'm going to change the sign of these two elements. So this would mean that this is going to be with a positive sign, A2 sine of theta 1 plus theta 2, and this is going to be with a negative sign written down. So in order to make room, I'll shift it a little bit upwards. So this is going to be minus A1 cos of theta 1 minus A2 cos of theta 1 plus theta 2. So this is your adjoint of this matrix, but you still have to find out what is going to be the determinant. So adjoint is known, determinant is needed to be computed. So I'm going to use the same expression for Jacobian to compute the determinant of this as well in the next slide. Now I can start from this Jacobian expression once again, and in order to make use of it in a better way, I'm going to use a shorter version or shorthand notation of the whole matrix over here. I can write this as the first term as minus A1 And sine of theta can be in a shorter way written like this, sine of theta 1. And then you have the other minus a2 sine of theta 1 plus theta 2. So this is a shorter notation of the full expressions. So I'm going to use it because in order to make this whole subsequent derivation much more easy to comprehend, we will need that. The second element is going to be minus a2 sine of theta 1 plus theta 2. The second row is going to become a1 cos of theta 1 added with a2 cos of theta 1 plus theta 2. And then you have the last element to be a2 cos of theta 1 plus theta 2. So I'm going to make use of this arrangement in order to compute the determinant of Jacobian. Now you know the formula for the determinant. This is going to require this multiplied with this element minus this with that. So with this realization that I'm going to use this shorter notation, I'll quickly try to handle it. So this is going to become a2 cos of theta 1 plus theta 2 multiplied with minus a1 sine of theta 1 minus a2 sine of theta 1 plus theta 2. And then you have minus sign, minus minus plus a2 sine of theta 1 plus theta 2 multiplied with a1 cos of theta 1 plus a2 cos of theta 1 plus theta 2. Now I'm going to expand it. So this is going to become like a1, a2 with a negative sign cos of theta 1 plus theta 2 sine of theta 1. And then you have minus a2 squared cos of theta 1 plus theta 2 sine of theta 1 plus theta 2. And then you can move on and see what is happening on the other side. This is going to be equal to plus a1 a2 cos of theta 1 sine of theta 1 plus theta 2, first element, and the second element is going to be plus a2 squared cos of theta 1 plus theta 2 sine of theta 1 plus theta 2. Now you can readily identify that you have this term a2 squared cos of theta 1 plus theta 2 sine of theta 1 plus theta 2 appearing over here, but the same term appears over here but with the opposite sign. So you can obviously cancel these two out. So I can rewrite the whole expression once again. This is going to be minus a1 a2 cos of theta 1 plus theta 2 sine of theta 1, and then you have plus a1 a2 cos of theta 1 sine of theta 1 plus theta 2. Now I can recall that the expressions that I already know, the trigonometric expressions, something like this, that cos of theta 1 plus theta 2, which is equal to cos of theta 1 plus theta 2, that can be written like in an expanded version like this, cos of theta 1 into cos of theta 2 minus sine of theta 1 into sine of theta 2. And similarly, sine of theta 1 plus theta 2, which is equal to sine of theta 1 plus theta 2 in expanded form, to be equal to, this was cos of theta 1 into sine of theta 2, and now you have the same sign over here, positive, cos of theta 2 sine of theta 1. So I'm going to use these expressions, these two expressions in this expression. So this would mean that you have this thing to be equal to minus a1 a2. Now I'm going to use cos of theta 1 plus theta 2 expanded form. So this is going to be cos of theta 1 cos of theta 2, then you have sine of theta 1 written down, and then you have minus minus plus, which is going to be a1 a2, then you have sine of theta 1. Actually you have another sine of theta 1, so I'm going to write down sine of theta 1 squared, and then you have sine of theta 2. Now the second term, which is I'm going to box it over here this term now. So that can be written down like this, that you have plus a1 a2. Then I'm going to use cos of theta 1, and then I can add the expanded version of it, the sine of theta 1 plus theta 2 expression, which is going to be cos of theta 1 squared sine of theta 2, and then you have once again plus a1 a2, and then you have cos of theta 1, then you have cos of theta 2, then you have sine of theta 1. Now you can identify that you have, let me use a different color over here, you have this expression where you have a1 a2 cos of theta 1 cos of theta 2 sine of theta 1, and the same one appears but with a positive sign on the other side, with opposing sign a1 a2 cos of theta 1 cos of theta 2 sine of theta 1 in the last term. So obviously you can cancel these two out. So as a result of that, you can rewrite the remaining expression, which is going to be a1 a2, and obviously you can see that sine of theta 2 is also there, which is common in both of these expressions. So I'm going to write that one down, and in the brackets I can find out, like, you have sine of theta 1 squared plus cos of theta 1 squared, and that obviously is equal to 1. So this would mean that the determinant of Jacobian turns out to be equal to a1 a2 sine of theta 2. And we've gone through this long derivation not without purpose. The idea was not to make you understand how to take the determinant, but to identify that you're going to left with this expression which has got a meaning associated with that, a physical meaning, which we're going to explore in the next slide. Now see, we started our inverse velocity kinematics discussion with this expression, that you have theta dot vector of joint velocities to be equal to Jacobian inverse times the given end effector velocities. Now that was expanded to give you the expression like it is equal to a joint that we have computed already of Jacobian divided by the determinant of Jacobian times the end effector velocities. Now, since determinant is now known, I can rewrite this expression in this fashion, that you have theta dot to be equal to 1 over determinant of Jacobian, which is equal to, in our case, a1 a2 sine of theta 2 multiplied with a joint of Jacobian that we have already computed. I need not to rewrite it again, times the end effector velocities. Now see what is happening over here. Now if I say to you that for special case, when you have sine of theta 2 to be equal to 0, that would mean that theta 2 is equal to 0. So in that case, you have this whole expression to be presenting a divide by 0 situation, and that is going to be troublesome, which would mean that you have theta dot to be equal to 1 over 0, and then you have a joint of Jacobian times the end effector velocities. Now see what is happening over here. So in that case, when you have the finite desired end effector velocities, if this situation arises when theta 2 turns out to be equal to 0, it is going to give you infinite or very big undesired joint velocities. What does that mean? Joint velocities means that your motors are going to run at a specific speed, But if it is infinite speed, your motors are running or trying to run at a very big, very high speed, which is going to be troublesome. So in that case, you have a singular situation or a singular configuration. So this is going to be another issue associated with the differential kinematics, that you have to find out these singular configurations for which you have a situation which is not ideal situation. So you need to avoid those. The physical meaning of this situation, when you have sine of theta 2 is equal to 0, which means theta 2 is equal to 0. This would be the situation where you have the arm extended fully. And obviously you can see that at this particular stage, instantaneously, the robot turns out to be kind of a reduced version of a 2DF robot. So it reduces in terms of its instantaneous situation to a 1DF robot. At this instance. And that's why it is a situation which is going to kind of reduce the capability of the robot. So that is needed to be avoided in robotic manipulators. So that's why all the discussion corresponding to this and all the other robots, more complex robots, in terms of identifying the singular configurations are going to become much more important. And we are going to handle that as well. The fourth major problem is corresponding to planning a path and finding a trajectory. So let's discuss it. Considering the scenario once again, that the robot is required to grind the surface up, starting from point A, going all the way to point B, moving over the surface S. And in the starting instance, you consider that your robot is parked at point A, right over here. Now, once the grinding at point A has been accomplished, you need to move to the next point and perform the grinding over there, and then to the next point, and then to the next point, and so on and so forth, eventually reaching to point B. So in that sense, you are going to subdivide the whole path into smaller segments or discrete segments. And that is the task of path planning, that you subdivide this whole path into discrete segments which the robot can follow. So this is going to be an important aspect to be handled as well, because this is going to give, once translated, the reference signal to the robot in order to achieve all those points in the workspace. Now, in addition to that, oftentimes what happens is that the time information is also needed to be added in this situation. What does that mean? You would say that you're going to start from point A at T0, but then reach to the next point at T1, and then at T2, and then the next point at T3, and eventually reaching to point B at some specific time, in a specific time like Tn. So in that sense, you are going to follow a specific velocity or acceleration as well. Oftentimes it becomes like when you're going to start your journey, you're going to accelerate and then perform certain operation in the middle at a constant velocity, and then decelerate when you are going to very close to your final point. So that kind of trapezoidal mode of action may be important in certain cases. So when you add the path information with the time information, this gives you the concept of trajectory. So in trajectory discussion, we generally consider two aspects. One is the generation of trajectory, and then in terms of control, the tracking of trajectory by the end effector. Now this is going to be, in that sense, a very important exercise to handle, because this is going to give you that realization that in the workspace, if a task is defined, how you're going to plan that activity so that the robot performs it in a specific way, in an appropriate and effective way. And then there is another problem. That problem is that generally the task is defined in the workspace. So that workspace is being shown over here. And you can identify that because this is the X coordinate over here, and this is the Y coordinate over here. And robot is parked right in the middle of it. Now, generally what happens is that when you have to perform, let's say, pick and place exercise, you define your exercise in the workspace. When, for example, you need to perform like this end effector should be moved in a specific way on a specific trajectory, you define that activity in the workspace. Now, in other words, workspace is defined as the volume swept out by the end effector. But what is problematic in this particular scenario is that the robot does not really understand what is the workspace. It understands what is the configuration space, or the space corresponding to the joints. For example, there is one joint over here, there is another joint placed over there. So these two joints are going to become understandable, or these are the points which the robot can understand, and that is what we call configuration of the robot. So how this workspace should be transformed into a configuration space, that is going to be an important aspect to be considered as well. So now you can observe that in the diagram that you can see on your right, you have Q1, which is corresponding to the first angle, and Q2, which corresponds to the angle of joint 2. So now you can see that the task is going to be defined in the workspace, but that is needed to be transformed into the configuration space so that the robot can understand it. And from configuration space back to the workspace, this transformation may also be needed. So how are you going to handle that? That is another major issue to be handled. Now, in certain cases, you need to make it even more complex, because in this case, you can see an obstacle placed over there. So if you have obstacles in the workspace, how are you going to avoid hitting those obstacles when the robot is only able to understand cues or configurations? So in that case, you have to transform this obstacle into the configuration space and define corresponding to Q1 and Q2 where this obstacle is. And then you have to label that area in the configuration space to be a no-go area or configuration space obstacle where the robot should not go. So in that particular sense, it is important for you to realize that the task is going to be defined in the workspace, but that is needed to be transformed into the configuration space where the robot can ask the actuators or joints to move in a specific way. And then you have to go back to the workspace to see whether the job is being done or not. So that is going to be another important aspect to be handled in this activity. A robotic manipulator generally is a blind machine, but when you add a camera to it, it is going to observe what is happening around it, and that is another issue to be handled. Generally, there are two paradigms. One, what we call camera on top paradigm, and the other one what we call camera in hand paradigm. So this image that you can observe over here is camera on top. So in that case, you can see that the camera is somewhere placed over here, and it is observing the whole scenario, and these dashed lines are indicating what is the field of view. Now you can obviously see that the field of view is in a rectangular form over here, where there are keys placed in different random orientations, and the robot is required to pick these keys up and place them in these slots one by one in a specific orientation. So what does that mean? It means that the camera is needed to ask the robot or guide the robot to pick up a particular key at a specific location, change the orientation in a sense that it once again matches with the slot in which it has to be placed, and that is the task uh, generally reserved for robot vision. So it is not the space to further dig into how we're going to achieve that, but generally in this particular paradigm there are certain issues. And one of the issues is that when camera is on top, and if the robotic arm is hindering the view, then it is the occlusion problem that you're going to observe. So view is going to be occluded. But the benefit is that because the camera is fixed, it is on top, it is observing the same rectangular field of view, so it is not going to require any recalibration or reorientation or re-registration of the images. So in that sense, it is going to be kind of a fixed field of view which is needed to be handled. So that is one good thing to have. But the problem of occlusion can be avoided if you place the camera close by the wrist or close by the gripper. It is called camera in hand paradigm. And you can see that right over here. So in that case, the robot is not going to hinder the field of view of the camera, and that is going to greatly help uh, understand the situation. But there is an associated problem with that, and that is when the robot is going to get closer to any object to be picked up, the object is going to grow bigger. And when the robot is going to have a rotation or reorientation, then obviously the orientation of the object is going to change. So growing something bigger as you get closer to it is going to be another problem, and reorientation is going to be another associated problem when you opt for camera in hand paradigm. So as you say that generally, or you hear that there is no free lunch, so this is kind of a similar situation. And now the sixth problem is that of robot dynamics. And in that, you're going to add kinematics with the other factors like inertial and gravitational and applied forces and torques in order to come up with a more complete picture of what is happening in the robotic manipulators. So in kinematics that we have discussed so far, we are only concerned about the motion, but without forces or torques associated with it. But when we say dynamics, we are interested in that. So this is going to be the story of motion, but with forces and torques associated with it. So that's why it is going to be an important aspect to be considered. Now, in addition to that, just consider that in this particular case, if you have length A1, this is going to have a point where this whole mass is centered, and that is going to be like heading downwards. And similarly for length A2, you have the mass of this link going downwards as well. So this may be like M1 G, and this is going to be M2G. And then because these links are rotating as well, this link is rotating as well, so this is going to generate a moment of inertia as well. So there is going to be J1 and J2, something like that. Now consider that you have a grinding wheel as well. So this grinding wheel is also going to have a rotation. So this is going to be something like JW as well associated with it. Now in addition to that, when this grinding wheel is going to have an interaction with the surface, this surface is going to have some sort of input given to the whole scenario. some disturbance given to the scenario. So this is going to be also an important aspect to be considered. Now, up until now, we have discussed quite a few things, but we have not discussed how the joint is structured. So what is happening inside this joint? So inside this joint, you are going to have a motor, you are going to have possibly a gearbox, you are going to have some sort of coupling, you are going to have some resistive elements like bearings and all that. So all these aspects, when added together, is going to make this whole dynamics of the joint difficult or different as well. So when you add all those aspects together, this is going to be uh, when you consider the dynamical response of the robot. And that is going to give you a set of equations which are going to have this kind of shape, that this is going to have an inertia matrix that is going to be dependent on thetas, but this is going to have the angular accelerations added with uh, a derived matrix from obviously the inertia matrix, but also it is going to account for the displacements and the velocities, and that is going to be multiplied with velocities as well. So all the centrifugal aspects and Coriolis factors are going to be added in it. And then you're going to have some sort of aspects coming in from the gravitational side, and that is going to be applied equal to the generalized forces or torques, something like that. So you are going to have a set of equations which are going to have this kind of shape, and this is going to account for, in that sense, two aspects, like kinematic aspects and it is going to account for the dynamic aspects as well. So with this realization that this is going to make this whole activity even more complex, uh, we will register at this particular stage that this is a major issue to be handled. At this particular stage, we are just considering a simple two-link manipulator, but when you have uh, an n-link manipulator, you are going to carefully handle this whole activity, and that is going to be one important aspect to be considered. Hold on, guys, we are getting closer to the final line. The seventh problem is that of position control. And as the name suggests, that you have to follow a specific path, but accurately and reliably. And that is going to be a major issue corresponding to the control paradigm. In a robotic manipulator, you are going to have joints. These joints are going to have motors in them. So this is going to be joint. This joint is going to receive the information from the controller, and it is going to produce an output. So output generally, because it is a revolute joint, it is going to be in terms of theta, for example. This theta is needed to be picked up or measured using some sort of sensor, probably an encoder, which is going to provide this signal back to the controller. In a controller, you are going to have a summing junction, if you consider it to be in a block diagram, and that is going to compare this feedback with a minus sign with a positive signed reference signal. And this reference signal, because it is the angular displacement, it is going to be in terms of angular displacement as well. So this reference signal is, when given to the controller, it is going to be compared with the feedback coming in from the encoder, and that is going to be given as an error signal to the controller. And this controller is going to allow or generate that requisite signal, which is going to allow the joint to move in a specific way. So this is a conventional control loop. You have seen it so many times, so need not to overly repeat that. But this concept is worth repeating because you have to identify that there are certain aspects. For example, over here you have a sensor which may have a noisy signal or noise added to it, or a noise added to it as well, here as well. And then, for example, you may have some disturbance added to the system at this particular case. For example, a disturbance torque is added to it. So probably you need to handle that as well. And then because you have multiple joints like joint 1, encoder 1 and control 1, which is going to make this as theta 1 and this theta reference 1. Similarly, you are going to have multiple similar control loops for joint 2, generating theta 2, giving feedback through encoder number 2 back to the controller, which is also a controller number 2. And that disturbance torque is also going to be differently structured, probably. So in that sense, the theta reference 2 is needed to be given to this controller, which is going to allow this second joint to be controlled as well. And that is also going to have its own problems corresponding to noise and all that. And from an operational point of view, you are going to follow a trajectory. So this is going to be trajectory or path, but that is going to possibly add certain disturbances which may have disturbances. So for that reason, you are going to be extra cautious that how you're going to allow this robot to move accurately over the surface starting from point A going all the way to point B, achieving all these points in the middle of it accurately and reliably. So that's why the position control problem is going to require the issues corresponding to tracking problems, the issues corresponding to rejecting the disturbances, the issues corresponding to handling the noise, and the associated issues to be uh, appropriately handled. So that's why the position control problem is going to become a major issue to be resolved. And obviously, force control is another problem which is going to be important. Grinding is being done at this particular location. Consider for a while that the grinding wheel is exerting more force than the required force. In that case, obviously, the joints over here and over here are going to experience the resistive force of that. And also the surface is going to be not appropriately cleaned or prepared. And if for a while you consider that the force applied over there is not the required force, it is less than the required force, in that case probably you will spend more time cleaning the surface up. So for that reason, the force is needed to be controlled whenever you have such kind of operation to be performed by the robotic manipulators. And that is going to account for quite a few other possibilities as well. For example, in our own lab, we are making one collaborative robot, and this robot is when needed to interact with humans, it needs to be safe enough. It needs to adjust its own movement whenever there is a human interaction with that. And for that reason, we are implementing impedance control paradigm in there. So there are going to be different ways in which you execute this force control problem, and that is going to be another important aspect to be considered in this whole discussion. So these are the major issues, but these are not all the issues. There are numerous other problems as well. For example, there is a wide range of possible problems coming in from the grasping and gripping domain. There is a wide range of problems associated with programming. From a robotics standpoint, we have not discussed for example, the compliance in the links and in the joints. We have not considered redundancy. We have not discussed from a control standpoint the robustness. We've not considered quite a few other things from operational standpoint like payload, speed of operation, stuff like that. So there are quite a few other issues from a conventional standpoint, and obviously from the modern robotics standpoint, there are some other issues as well. For example, artificial intelligence related tasks, how you're going to allow the robot to learn new things, and quite a few other aspects associated with modern robotics. But we have not discussed those. But these are equally important issues to be resolved. Now, in nutshell, we are going to consider this whole situation to be in one possible case presented like this, that for N-link robot, we are going to have the control loop corresponding to all the joints, all the N joints. So in that case, that is going to be something like you have joint 1 producing an output. That output is sensed, fed back to the controller. But this joint is going to produce an angular displacement generally, if it is the revolute joint. So this is going to be theta 1, as mentioned earlier. And that control scheme is going to require a reference theta to be given to it. That is going to be theta 1 reference. Now we have considered quite a few other things as well, like the sensor module over there, the disturbance added over there. So consider those as well. So this is corresponding to joint number 1. Similarly, we will do that for joint number 2. Producing an output theta 2, getting sensed, fed back to the controller, controller adjusting itself corresponding to the requirements. But that would require theta 2 like given as a reference as well. And we will keep on repeating this whole activity all the way to the nth loop, or for the nth joint. So this is the nth joint producing theta n, getting fed back. In the nth joint controller. And this is the reference theta n reference given to it. Now consider what is going to happen when you get all these thetas available. So in that case, there is going to be a big block. This block is going to be receiving this information of the thetas, and it will produce the output in terms of x and y and z, if I may say that. And that is what we call the the forward kinematics exercise. Now in the forward kinematics, remember, we are providing all these thetas in it. So all these expressions that you have written down over there, like x2 to be equal to a1 cos of theta 1 plus a2 cos of theta 1 plus theta 2 is going to be incorporated in there. So there is going to be one building block which accounts for the position. So there is going to be that module inside the forward kinematics module. There is going to be another module corresponding to velocity. So forward velocity kinematics is going to be handled in there as well. And that is going to produce the x dot, y dot, and z dot, stuff like that. But it will require this information given to it in terms of theta dots as well. And that is going to be theta 1 dot produced over here. So speed control paradigm is going to be, when implemented, you are going to get the information corresponding to the angular speeds, theta n dots. So these are going to get into the velocity block, and they will produce how the end effector is having its velocities executed in the task space. And similarly, if you are going to have the acceleration needed, that will be added as an additional module in that. So forward acceleration kinematics is going to require the theta double dots as well. So this is going to have theta 1 double dot, this is going to have theta 2 double dot, it's going to have theta n double dot produced in there as well. Now on the left side as well, you can see that you've just like written down these reference signals in terms of angular displacements, but obviously because you have the velocity and acceleration added in it, so those are going to be added as reference signal to that as well. So these are being generated from a similar big block, but actually internally there are going to be quite a few different things, what we call inverse kinematics block. Now in these inverse kinematics, you are going to have these modules corresponding to position. So all these expressions that you have computed, theta 2 dot to be equal to tan inverse of something, and theta 1 dot to be equal to tan inverse minus tan inverse of the other expression, and all that. So those are going to be embedded in it. Similarly, you are going to have a module for the velocity. You are going to have another module if needed for the acceleration as well. So these are going to provide the outputs which are going to be provided to the control paradigm as reference signals. But there is another aspect to be addressed in there, and that corresponds to what is going to be the task space or task which has been translated into requisite signals corresponding to the inverse kinematics blocks. So this inverse kinematics is going to require x, y, and z's, and x dots, y dots, and z dots. But how are you going to transform the task into these vectors? So that is going to be the block where you have the path planning and trajectory generation. So that will be giving you all these requisite reference signals which are going to be fed to the inverse kinematics block, which then when solved are going to provide the requisite reference signals to all these joint controllers. And remember, this is one of the control paradigms. This is not the only paradigm. There are multiple different ways to handle the control of N-link robotic manipulators. But this is just like going to give you an overview of how things are correlated with each other. And I should emphasize that the forward kinematics is needed to be resolved, is needed to be solved all the times, in a second multiple times. And similarly, inverse kinematics is simultaneously required to be solved again and again. So all the issues corresponding to singularities, existence of a solution, uniqueness of a solution is going to become important in the inverse kinematics as well. But inverse kinematics itself is dependent on how path planning and trajectory generation module has given this task in a structured form to this module. So you have to consider all these issues in conjunction with each other. These are not isolated issues. These are all related with each other, and that's why these are needed to be handled and resolved in this whole course. And as a disclaimer, I should also emphasize that we have not discussed operational issues such as troubleshooting and maintenance and recalibration and how you handle these faults and stuff like that. This is going to be some other course which may address that, but this particular course is primarily structured to give you the kinematics and dynamics and control of such robotic manipulators. So that's why that paradigm, that domain boundary is needed to be very clear in your minds. We are not discussing all the aspects, we're just considering one particular domain which is important. So this is end of our discussion. We have spread out this stuff. We have kept the discussion shallow. We have not got into difficult derivations and difficult manipulators. We have kept it simple, but we have covered all the major issues that we wanted to cover. And this is it for today. If you have any questions, you can always raise those. And until next time, bye-bye.